Good morning, dear girls. Welcome back to our sessions. So I'm happy that you took
Good
up
morning,
your
ma'am.
test. Very good morning. I'm happy you took up your test and you've written answers good. I don't want to share the marks on the group, so I will share it to your numbers. And when you come to college, we will give you the marks in total. Okay. So personally, your marks will be sent to you. You can have a look. So today's class, we will move on to the next chapter, that is electrostatics. Chapter 1 and 2 together comes under this topic of electrostatics. So what we are going to study in this chapter is, we are going to study about what is electric field. You're going to study about electric field intensity and electric field strength. Then we are going to see what is electric field intensity due to a point charge. Fourth point will be superposition principle. We are going to learn these electric lines of force. These will be diagrams. Fifth point. Due to a point charge, due to a dipole, equal and like charges, uniform field, how to draw lines. That is what we are going to study. Then we will see what are the properties of electric field lines. Next point will be about electric dipole. Then we will see about what is electric field intensity due to an electric dipole and work done. So these are the points we are going to discuss in this chapter of electrostatics. Chapter 1 is electric charges and field. Chapter 2 is electrostatic potential and capacitance. Both together comes under this topic of electrostatics. So we'll move on to our classes. The first definition what we're going to learn is what is electric field. So observe carefully. Electric field is a region of space around a charge. A charge can be positive or it can be negative. The region of space around the charge or a system of charges. It can be a single charge or it can be a system of charges within which other charged particles experience electrostatic forces. That is called as electric field. I am repeating it. Electric field is a region of space around a single charge or a system of charges within which other charged particles should experience that electrostatic force. So that region around a charge or a system of charges where other charges can experience their force, we call that as electric field. I gave you an example of magnet in current electricity chapter. You keep two magnets far away from each other, they will not attract. As you bring them closer and closer and closer, you can see the force of attraction becomes stronger. That means a magnet, if it is placed in a position in a certain region surrounding it only, it will have maximum force. Same way, there it is called as magnetic field, and here we call it as electric field. Keep it very clear. It is a region of space around a charge or a system of charges within which other charged particles will experience electrostatic force. Clear? Now the next thing what we are going to see is theoretically how to write it in a book. We will tell electric field extends up to infinity, meaning it moves on and on, but practically it is limited to a certain distance. Theoretically means book wise we will tell it is infinity, but we know when we do experiments, field will not be there everywhere, only to a certain distance it is limited. Just for you to keep in mind. Theoretically, electric field is up to infinity, but practically it is limited. Your next point will be electric field strength or electric field intensity. So when we talk about electric field intensity or electric field strength, both words are same. You can use the word strength or you can use the word intensity. Electric field strength at a point due to an electric field is the electrostatic force per unit positive charge which acts on a vanishingly. See, instead of this word vanishingly, you can also tell on a test positive charge. I'll tell you what is a test positive charge. So electric field strength at any point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive charge placed at that point. So what is this field strength? It is nothing but it is the electric field or electrostatic force per unit positive charge. For one charge, what is the electric field? That is what you're going to see in the topic called electric field strength, or you can use the word electric field intensity. How much force is needed for one positive charge? That is called as your electric field strength. I told you vanishingly means it is disappearing. Small positive charge, a single positive charge is what you have to consider here. The electric field strength or intensity is nothing but it is the electrostatic force per unit positive charge, and it has to act on a test charge. Test charge means a small charge which is taken into account where it will not have more force. Only for testing we are going to use that charge. So unit positive, 1 unit will be the value of the charge. You just look at this diagram. We are having a test charge here denoted by plus Q. And I'm having one more charge here. You have the value to be written as plus Q naught. So one charge is unit positive, the other one is plus Q naught. Now, what is this electric field strength? If you see, you will have a line here which is connecting plus Q and plus Q naught. Electric force will act in the direction along the charge. Look carefully, both are positive. So what do like charges do? They will always repel against each other. So you can see plus Q is here, plus Q naught. This is called as your test charge. If you have a positive charge and the test charge is also positive, then electric field will be in the positive direction. Check the second example. You have a negative charge here, okay, and test charge. Keep in mind, test charge will always be positive. Here also it is plus Q naught. Q naught means it's going to be the test charge. In first figure, I did it for a positive charge. You can see F direction is along the positive direction. Check for the second diagram now. You have a line connecting both, but what will be the charge of your electric field? It has to be in the reverse direction. Reason, negative and positive will always attract each other. Positive and positive will only repel. So for a positive charge, field direction and charge direction will be the same. For a negative charge, field direction will be positive, charge direction will be negative. Okay. So our next point, what we are going to see is what is Q here means it is the source charge. Q naught is called as the test charge. F is the force and E will be your electric field. If you want to write it in terms of your limit, there's one topic in mathematics you'll be learning about differential or limits. There, electric field is defined as, look at the definition here, electric field is electrostatic force per unit positive charge. So I can write this F divided by Q. Why we use this delta symbol is I'm using limits here. Delta or this triangle is called as delta, and that is the charge will have some change. That is the meaning for the delta. And this limit will be delta Q should be tending to 0. This arrow mark means it is tending to 0. We use the term, it is vanishingly small. It's becoming smaller and smaller. So tending to 0 means from a higher value, it will reduce and reduce and reduce and become 0. See, I'll give you a best example here. You put your phone on charge. Okay, you've charged it to 100% battery. Then you remove it from the plug. You keep on using it. What happens to the charge level in your mobile? From 100%, it will come down to 90. After 2 hours, maybe it will come down to 60%. You keep on using it for 4 hours, your battery charge will show it is very less. Go and recharge again or put it in the plug again. So as you are using the mobile phone, the battery charge becomes lesser and lesser and it gets drained up. The same way, here also charges, as we are applying force on them, it will keep on reducing. So when it is reducing, it will tend to become to zero, or finally at a point it will become to zero. Today morning you charged your mobile. Say by afternoon, after 3 classes, will you have the same charge on your battery? It is going to reduce. So it is becoming lesser and lesser, and it will become equal to zero. That's the meaning here. It is vanishingly a small positive test charge. Mathematically, if you have to write the formula for electric field, E equals limit delta Q tending to zero, F divided by delta Q. F is the force, delta Q is your charge. And definition is electrostatic force per unit positive charge acting on a small positive test charge. So that is the definition what you have. If you want to write another formula for this, then E equals F divided by Q naught. I'm removing this delta sign. Since Q is tending to zero, I can write E equals F divided by Q naught. That is the second formula. Or you can also write E is equal to 1 divided by 4 pi epsilon naught. The symbol is called as epsilon naught. We call it as relative permeability of free space into Q divided by R square. This is the general formula. If you write it in vector form, you should represent this R, and this is a cap on top. That is called as a unit vector. Its value will be equal to 1. 1 multiplied by anything will give you 1. So what we do here is, only if this vector symbol is written on top, this R cap will be there. Otherwise, generally you will write E is equal to 1 by 4 pi epsilon naught Q divided by R square. This statement is also called as Coulomb's law. You can write this in your book. So E is equal to 1 by 4 pi epsilon naught Q divided by R square is the formula for Coulomb's law in general. In vector form, you have to just add this R cap. So there are 3 formulas. One is in terms of limit. The second one is just in terms of test charge, that is Q naught. Third formula is in terms of your Coulomb's law. And all these 3 formulas are for what is the formula for electric field strength or electric field intensity. This test charge is considered to be vanishingly small because its presence should neither alter the configuration of the charges and thus the electric field. Test charge, why we call it as vanishingly small, means it is only to test. Now in this region, this charge value is 5 coulomb, for example. Then this test charge should not alter the configuration. It should not have any effect. The total system charge also will be 5 only. Just to test it, we are going to have here. That's why we are using the term vanishingly small. It should never alter the configuration of the charge or the electric field. It is only a small value which is considered for testing. You have a note here. Since Q naught is taken positive, the direction of electric field is along the direction of electrostatic force F. This is what you saw in your first diagram. The second one is electrostatic force on a negatively charged particle will be opposite. Your second one is the correct thing which you have done. So what you have to do here is, if it is a positive charge, E will be along the direction. You can see it in this diagram here. It is along the direction. If it is a negative charge, it will be in opposite reaction. Direction of electric field will be opposite. So those 2 points you just keep in mind. Electric field is a vector quantity. What is a vector? It should have both magnitude and direction. That's what is given here. Whose magnitude and direction are uniquely determined at every point in the field. 1 mark question. Is electric field a scalar or a vector? You have to mention it is a vector quantity. What is SI unit for electric field is Newton per coulomb. Girls, you should just keep in mind when we write the symbol. If I'm writing the symbol, it will be in capital letters, capital N and capital C. If you write the spelling, it should start with small alphabets. See, Newton is not capital in here. I'm writing it as small n. So SI unit for electric field is Newton per coulomb, or N C to the power of -1. When we use the term per, you can write it as C to the power of -1. So learn up this. SI unit for electric field is Newton per coulomb. The next point what we are going to study is what is electric field due to a point charge, that is due to one charge. Before we go into this topic, I have questions for you. What is the SI unit for electric field?
Newton -1.
Coulomb, ma'am.
Newton per coulomb. Very good. For a positive charge, what is the direction of electric field? I will follow the names.
Ma'am, your voice is not clear, ma'am.
The host unmuted everyone.
Okay.
Vector quantity, Nita.
Vector quantity, ma'am.
Okay. You tell me I will call out the name and then call you. I just want to know what is the direction of electric field for a positive charge. Devika, Aisha, Steffi, Margaret. Is it in the same direction or opposite direction? If it's a positive charge, is it in the same direction or is it in the opposite direction?
Same direction, ma'am.
Same direction. Very good. If it is a negative charge?
Opposite direction.
Opposite
direction, ma'am.
Okay. Very good. We'll go on to the next topic. So we're going to see what is electric field due to a point charge. See, I'm going to draw a graph here. I want you to consider X, Y, and Z axis. And we have a center point here denoted with the symbol O that denotes your origin. Coordinates at this point will be 0, 0. Now when we take this graph and I place a unit positive charge at the point O, plus Q is the charge. When we tell unit positive, its value will be +1. We are going to do a derivation, small formula for this. You consider a point P, and that point P is in your XY plane. You can see this is X axis and this is Y axis. Coordinates will be denoted by X, Y, and Z. There you consider a test charge. The test charge is denoted with the symbol +Q0. So at the origin, you have one charge which is +Q. At a point P, we have one more charge which is called as the test charge. And you can see the electric field is in the direction indicated by F vector. Now if I take the distance between +Q and +Q0 to be R vector, you can see the arrow mark which is moving. We are considering two charges separated by a distance small r. Then your formula will derive like this. Force exerted on Q0 by Q. Keep it clear. Force exerted on the test charge by the source charge will be given by the formula F is equal to 1 divided by 4 pi epsilon naught. This is common. This is your constant thing what you have. 1 divided by 4 pi epsilon naught. What are these two values now? One is Q, the other one is Q0. Plus sign I'm not indicating. So product of the charges is Q into Q0. What is the distance between the two? You can see the distance between the two is R square. Okay, according to your Coulomb's law, the force of attraction or repulsion between any two charges will be directly proportional to the product of the charges, and it will be inversely proportional to the square of the distance between them. Is that clear? So we are going to see force will be directly proportional to the product of the charges, inversely proportional to the square of the distance between them. If you have to remove the proportionality sign and introduce a constant, that is where we write 1 divided by 4 pi epsilon naught. That is called as a proportionality constant. So what you have to write here is force exerted on Q naught by Q is given by the formula F equals 1 by 4 pi epsilon naught Q into Q naught divided by R square. Or we can also write it as F is equal to 1 divided by 4 pi epsilon naught Q into Q naught divided by R square into R vector. So this is not R cube. I'm writing it as R square into R vector. Unit vector will be replaced by the symbol a normal vector R. So what is unit vector value? I told you it is going to be 1. So if you want to write it as a vector, we will multiply and divide by R. So if you multiply here, R square into R will become R cube. R into R, this value is 1. Unit vector's value is 1. 1 into R, you will get R. That's why we wrote it as R cube. I'm explaining it again. This is the general formula. F is equal to 1 by 4 pi epsilon naught Q into Q naught divided by R square multiplied by R cap. When you see this cap symbol here, it is unit vector and its value will be equal to 1. If I want to remove this unit vector and write it in vector form, multiply numerator and denominator by R because they can cancel out. So R square into R, when you multiply, it will become R cube. This value of R cap is 1. 1 into R, you will get this R vector. So this is how you have to write the formula for electric field due to a point charge. For this, the electric field strength formula will be, previous definition I told you, electric field strength is electrostatic force per unit positive charge. So we can just write it as E is equal to F divided by Q naught. Therefore, in vector form, E of vector R, I'm using the second formula. Force means F. Electric field strength means you should immediately change it to E. So E of R is 1 by 4 pi epsilon naught Q divided by R cube into R vector. Any guesses what happened to this Q naught? Kavishri? I'm in touch.
It got
Any guess?
cancelled, ma'am.
Yes? Little louder, ma.
Got
Cancelled.
cancelled.
What?
Q naught
What is Q
Q
naught? I
naught,
told
ma'am.
you it is a test charge. What is its
charge.
value?
0, ma'am.
Very good. It is tending to 0, we saw. So what is this tending to 0? Means little by little it will come back to 0. That's why this test charge is disappearing here. Very good, ma'am. So electric field strength is 1 by 4 pi epsilon naught Q divided by R cube into R vector as it is. Only thing, remember, force means F, electric field strength means it has to be E here. The next formula what we have, 1 divided by 4 pi epsilon naught Q divided by R square into R cap. R cap, when we write, denominator will automatically become R square. R vector, when you write, denominator will automatically become R cube. So those two differences you just keep in mind. So if you plot a graph taking R square on your x-axis and E on your y-axis, you will get a slope sliding from top to down. That is because as your electric field increases, the distance has to decrease. Keep that magnet's example in mind. You bring the magnet closer and closer, distance is decreasing. What will happen to the electric field or magnetic field? It will increase. So always electric field and the distance should be inversely proportional. That's why we are having the slope which is coming down. The electric field due to a point charge has spherical symmetry. What is the direction? One mark question in your competitive exams they can ask. Just for that sense, keep it in mind. It has spherical symmetry. That means it should move along a sphere. If Q is greater than 0, that is, if your charge is greater than 0 or if it is positive, then the field is radially outwards. I'll show you a diagram, you will understand this. Next point is, if Q is negative, then the field is radially inwards. Q is greater than 0 means it is positive. Q is less than 0 means it is negative. So we will see what is electric field in terms of the coordinates, that is x, y and z axis. So when you write that, E of r vector, r is in terms of distance, it is 1 by 4 pi epsilon naught q into r square we write. Instead of that you can write x square plus y square plus z square to the power of 3 by 2. So here what will happen is square and square root will cancel. We will have only 3 into your unit vector. So unit vector for x axis is I cap, for y axis it is j cap, and for z axis it is k cap. All these are only for your competitive exams. Just for reference, you can just keep in mind. Our next topic is superposition principle. Now what is the superposition principle is? Now when you have electrostatic force experienced by a charge due to other charges, then it is the vector sum of electrostatic forces due to the other charges as if they were existing individually. So let me give you an example here. Now there are 4 charges. I'm naming it as Q1, Q2, Q3 and Q4. What is the total force for all the 4 means? I will write it as total force is equal to Q1 plus Q2 plus Q3 plus Q4. So what I'm doing here, I'm taking the sum or I am adding as if they were the individual forces. That's the meaning. Superposition means if you have a group of charges, the resultant force will be equal to the sum of the individual forces. If there are only 2 forces, Q1 and Q2, what will be the superposition principle according to the forces? F will be equal to Q1 plus Q2. Meaning is, if you have a collection of charges, the individual force will be representing the total sum of your charges. That's the meaning. Keep it very clear. Electrostatic force by a single charge due to other charges will be the vector sum. I'm adding the electrostatic forces due to the other charges as if they were existing individually. That is, you have to take the sum of all the individual charges. This is what I told you. You have Q1, Q3, Q4, Q5, and you draw lines for that. Observe the diagram. Wherever you have positive charge, direction will be outwards. If you have negative charge, we have to consider it as inwards. Now what is this F12? Meaning it is a force due to the charge 1 and charge Q2. 1,5 means due to 1 and 5, due to Q1 and Q5. If you take this F13, it will be due to the charge Q1 and Q3. Like that, whatever number you write here, if it is 1, 2, it is due to the charge Q1 and Q2. Like that, force will be denoted keeping the 2 charges in your mind. That is the meaning for your superposition principle. 1, 2 means charge 1 and 2. 1, 5, Q1 and Q5. 1, 3, it is the force due to charge Q1 and Q3. So that is what is your superposition principle. Now when we can draw these lines like this, you can connect it in the form of the resultant. So you have F1 here, F12, 13, 14, 15. In all the forces, what is common if you see, one term is common, correct? So the first charge can experience forces on all the other 5 charges. That is, F11 will not happen. It will happen on force due to Q1 on Q2. That is F12. Force due to Q1 on Q3. This is force due to Q1 on Q4. And this is force due to Q1 on Q5. When I take the sum of all that, I generally denote it with the symbol 1, F1. So just keep in mind, superposition principle means you have to add all the individual forces in vector form, and that should be taken as the total. What we've written here is F1 is equal to F12 plus F13 plus F14 plus F15. The same thing if I write it as F2, it will be F21, F23, F24 and F25. Like that, for each force, what you write here should be the first number. All the remaining charges should be added up simultaneously. In vector form, if you want to write, it is 1 by 4 pi epsilon naught Ra minus Rb divided by Ra minus Rb the whole cube. This formula will be, you take for example, if A is 1, B will be equal to 2 to 5. That's why we write it as 2, 3, 4 and 5. If the force is to be found on the second charge, then what will happen? A value will be 2. B value will become 1. Then you will write it from 3 to 5. The interaction must be on the charge which is to be studied due to the other charges. So if you write F12, it is interaction of charge 1 due to the second charge. That is the meaning there. The charge on which the influence due to the other charges is to be found is assumed to be the floating charge and the others are fixed. So if I tell 1 and 2, first charge will be fixed, the second charge will be floating, meaning it can move. For example, if you take the reverse, the first charge is floating, then it will be repelled away by Q2 and Q4 and attracted towards Q3 and Q5. What is the reason is Q1 will be a positive charge, Q2 and Q4 are positive means it will repel. Q3 and Q5 are negative means it has to attract. Interactions between the other charges must be ignored. So we are not considering second charge or the third charge or the fourth charge. Only first charge, that is F12, F13, F14, only those charges will be considered. Superposition holds good for electric field also. It is not only for charge, for electric field also it holds good. Now what are these electric lines of force? Electric line of force, you can have it as an imaginary straight or curved path along which unit positive charge is supposed to move when free to do so in an electric field. So if you have an electric field, you see the charge is moving from the point A to B. How to represent it? You can draw an imaginary line. The imaginary line can be a straight line or it can be a curved line. So electric line of force is nothing but imaginary line along which a positive charge can move in an electric field. Electric field lines do not physically exist. They are not there, but only for imagination, for our understanding, we represent it in real life situations. So it can be a straight line like this, or you can take it in a curved form. Electric lines of force can either be in any direction. You just see this diagram. Electric lines of force due to a point charge. This is positive. Q is greater than 0 means it is positive. So you can see the arrow mark will be directed outwards. You have 5 chocolates in your hand. Somebody wants it. When you give, if you have 5 chocolates, you will be giving them more because you already have extra. You need only 1. So 4 can be donated. So when you give, your hand will be moving in the outward direction. So for a positive charge, always charges will be negative. Now I want 1 chocolate. I don't have anything with me. What will I do? I will receive. So when you have negative charges or when Q is less than 0, automatically charges will be directed inwards. Keep in mind, if it is positive, Q should be greater than 0. If it is negative, Q should be lesser than 0. Positive means arrow will be outside. So one circle you will draw lines like this, put arrow mark in the outside. When it is negative, you will put arrow marks in the inward direction. Size of the arrow represents only the strength. So this arrow mark will represent what is the direction of your electric field. Now see this diagram, you can draw it like this or you can draw it in the second way what we have. Second diagram shows the strength is more. The first diagram shows the strength is moving in smaller steps. That is the meaning for your electric line of force. If it is positive, arrow mark outward. If it is negative, arrow mark will be inward. Steffi, you have some doubt? Steffi, Margaret, you've raised your hand.
Yes, ma'am. Ma'am, I did not get the signal, so I logged out and again I log in, ma'am. Previous one, can you explain it once again, ma'am?
I'll do it to you. We are running short of time. I'll do it to you again in tomorrow's class and then continue. Okay.
Okay, ma'am.
So if there are two charges, how to draw electric lines of forces? See, one positive and you have one negative charge. See, I'm drawing the lines. Positive means lines should go outside. Negative means lines should come inside. So it will be a curved line. From positive it will start and it will come towards your negative end. So this is how you have to draw for electric lines of force due to pair of equal and unlike charges. Unlike means one should be positive, one should be negative, and we call that as a dipole. Observe clearly, arrow mark from positive will start and it will come towards your negative. And when it is coming towards negative, arrow mark should go inwards. You see here, it is inwards towards the charge. From here, it should be outwards. If they ask you draw a diagram for a dipole, this should be your diagram which you draw. And charges here are equal and unlike charges.